Alive. Oof. Okay, so that goes there. This goes there. This goes there. Okay. What is this? Hello, everyone. Whoever's in the chat. Oof. Oh. Is today Teacher's Day, Chris? I didn't know that. I forget about it every year. Good morning, Itamar. Good morning, Ethan. Good morning, Eric. I need a way to get this a little higher. I'm running out of thick books. Let's see. Oh, that's a real thick one. Okay. Look at this. All right. So I'm going to put my laptop in that book. And then maybe I could see my whole face this time. Oh, it's really heavy. Okay, how about now? Oh, this is so much better. What? Whoa! Okay. Good morning again, Jacqueline. Good morning again, Jonas, Sarah. Okay. Sup, Jared. All right. So it is 10:33, 6 minutes in. Let's begin. Okay, so I hope you enjoyed Mr. Ross's video and how he created an electric motor for us. I think that was super cool. I personally have never even made a motor. I was never like super hands-on-y, so yeah, I thought that was super cool, and I hope just seeing it work in action kind of made like the diagrams I was drawing here yesterday make a bit more sense. You tried it, it didn't work. Did you use the Sharpie, Itamar? So the thing is, you can read some more online guides about it, Itamar, but what you really want, you want a coil. You can't just have one circle of wire, because theoretically, like while like that should work, the more coils you have, the bigger the magnetic force will be, right? Because you just have more and more electrons. For each coil, you're basically adding, doubling, tripling, quadrupling the amount of electrons that are affected by the magnetic field, right? And too many coils make it too heavy and difficult to spin, right? So it's, okay. When is that assignment due? It's due at the end of the week, right? So, but just know that we are starting a new unit today, right? Ainava, you came late again, good sir. Yes, I think I made the solenoid too heavy, too many loops, right? Yeah. And the most important thing you have to do is what Mr. Ross kind of highlighted in the video, is to make the bottom half made of some insulator, right? And I think yesterday in class we went over why it's important to have it that way. And I think I previewed that Mr. Ross came up with a really pretty cool and creative way to do that. Yeah, and something as simple as like ink, like dried ink, serves as enough of a barrier, an insulating barrier, to cut off the current. Sharpie does work. That's what Mr. Ross used, isn't it, Mr. Ross? If you're in the chat. Okay, so but today we're done with magnets and we're moving on to the next topic, okay? Why is it April? I don't know. All right, so we are looking at waves today. Delicious. What's the example I like to use for waves? Okay, so I have this cord, I have this cable. Okay. So when you think of waves, like everyone in the chat types super fast, what's the first example that you think of when you hear waves? Like what is an example of a wave that you know? Spam the chat. Sound wave, sound wave, sound wave, sound wave. Really? Whoa. Ocean waves, light waves. Great. Those are like the light waves, sound waves, light waves. Wiggly wiggly. Yes, wiggly wiggly. Cool. All right. So let's get right to it then. So those are all really great examples of waves. And the waves I want to focus on right now are mechanical waves, right? So here's some basic properties of mechanical waves, right? So a mechanical wave this is a wave that travels through a medium. That's a vocabulary term. All right, the medium is the material through which the wave propagates, or the material through which the wave travels. So if I do this, I myself am the medium there for this wiggly wiggly, okay? A sound wave, the medium is air. An ocean wave, the medium is water, right? So it travels through a medium, right? And while it does so, and during which it moves particles in the medium. This is not a definition of a mechanical wave. It's something that's true about a mechanical wave, all right? The real definition of a mechanical wave, or something else that I would add to this, right, to come up with a more complete definition, is that it's the movement of energy, right? It's the transportation all right? So we all know that energy, total energy in any system is conserved, right? So that means if I lose energy, something else has to gain energy. And a lot of times, that transfer of energy from me to like whatever I'm giving the energy is achieved or transferred through a wave. So here I have some string, okay? It's a coiled wire, okay? And it's attached to my pasta maker, okay, my pasta roller over there, okay? And I'm going to send a wave pulse with my hand, okay, just like that. So, whoop, right? Whoa, do you see that? Whoop, right? So essentially what we have is, oof, right? I sent a pulse this way, right? So what's really happening? I lost chemical energy that turned into kinetic energy. And then all of a sudden, my hand doesn't have kinetic energy anymore. Where did it go? It went to the wave. And then that wave moved that kinetic energy and gave it to whatever was holding the rope at the other end. Because whoever's holding the rope at the other end, when that pulse comes, they'll go like, whoa, right? And they'll feel that kinetic energy. So the wave basically is a transfer of energy, okay? That's how I define a wave. It's a transportation of energy. Okay, so now let's get into some more specifics about like how the energy transfer works, blah, 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 blah. Okay, so here we have a wave, no big deal. And it's moving energy, right? It's moving my kinetic energy. The one thing you have to know, the most important thing about this wave is that here's a particle. Let me look at this particle, right? It's a molecule on my string, right? Or if this is a cross-sectional view of the ocean, like it's just one water molecule. When the wave passes through, this particle will go up and it'll go down, right? That is all it will do though. It will experience no net horizontal displacement. So if this is a rubber duck and waves pass by and they keep passing by, guess what? The rubber duck will never move side to side. It'll only go up and down. So while the wave travels through the medium, these wave particles, the particles undergo zero net displacement. The only thing that's ultimately displaced is the energy. The energy goes from point A to point B, but the particles themselves stay put throughout one cycle, right? Yeah, this is Saeed's unit. Where is he? Saeed, you in there? Huh? You vibing or not? Because these waves be vibing, okay? All right, so I am now going to turn over the page and go over some pretty important conventions that we use when we study waves, okay? And that'll be it. Today will be a really short lesson, right? I know some of us are reviewing for AP tests, like either the AP Physics exam or like AP exams for other classes. So we're going to keep the pace of this week a little light, all right? And I think I would have done this anyway. Changed the pace of the course to go a little slower, like regardless of the AP or not, just because I know we're getting a little tired, and it's summer now, and I want things to be slow and stuff. Okay, and just for a quick heads up, I posted an AP review problem, even though I hate the College Board and whatever. Like, I think this year's exam is a sham. I know some of you want the review, so I'm doing it because I love you guys. Type a quick yes if you're going to come tonight at 7:30 p.m. I just want to get I want to know what to expect. So just type a yes if you're going to come, and that's cool. I just want to know who's coming. And even if you aren't taking the exam, I think it's a pretty nice problem. So, all right, cool. Are all of you taking the exam as well? No judgment, okay? That's a private question. You don't have to answer that. Yes and yes. I see. Okay, then let's do a little review, okay? Here's the stuff about where. There are two representations of a wave, okay? Here's one. It's a literal picture of a wave, right? And in this, well, what you're really looking at it is like two sets of axes, x and y, right? This is a literal picture of a wave, and what you're really doing is just putting a ruler there and a ruler there, and you can kind of see the wave. And in this sense, you can measure certain things about the wave. You can, there are certain vocabulary, there's certain parts of the anatomy of the wave that you should know. For instance, like high points are called crests. Low points are called troughs. This height here is called the amplitude, right? The amplitude is like half the total height, right? Because it's defined as, we're going to get into why it's half, okay? Or why people say it's half. What I really say is this size is twice the amplitude, right? Semantic difference. And the wavelength. The wavelength is the length of a whole cycle, like the physical length, not the time length, not just the period, right? So, and I define a wavelength as the distance from crest to crest. This is one wavelength. It's abbreviated by the Greek letter lambda, which is the Greek L, because it's a special length, like L for length. So that's what lambda comes up. And or trough to trough, or this midpoint to this midpoint. It doesn't matter, right? You just gotta find the identical point, the identical phase point, and then go to the next one, and then that's your wavelength. All right. The second way to talk about your wave is as follows. Your position versus time of this particle, or of any particle in the wave. I'm going to pick this purple particle here, okay? And I'm going to draw the graph as follows. So what is this? What is the story of this graph? This says until the wave hits the particle, that particle is at a zero height. Then at some point in time, t1, I'll say t1 is when this part of the wave finally reaches that particle. Then the particle will dip down, right? When this wave is at when it's at this location, right? Then the particle will go down, right? And then it'll go down, and then back up, and then back down, and then back up, and then down, and then back up, right? So this tells the story of one particle in the medium. That's it. If this looks familiar, it's because essentially what this purple particle is going to do is it's going to act like its own simple harmonic oscillator. Yes, it's part of like a longer chain of things, but if you look at that particle alone, and only that particle, right? So like I can take these two things and say, hey, boom, what's that one purple particle going to do, right? It's just going up and down, right? And it's going to go up and down in a periodic fashion because this periodic wave is, just passing through it. Essentially, it looks and behaves like a simple harmonic oscillator, right? And that's the other way to look at waves and stuff, is to look at the oscillating behavior of a single particle in the medium. And the graphs look really similar, but they tell you two completely different things. One, they tell you identical information about the amplitude, right? Because what's this negative height? It's going to be the same as what that negative height is, right? So these graphs both tell you the amplitude, okay? So this is still amplitude, but now this length is different. This is not wavelength. Can someone tell me what this is? What does this length now represent from crest to crest? What does that represent? It's not a wavelength anymore. It's the period. Exactly. This is the time it takes to create one cycle. So if I'm shaking my wave like this, right, that's going to be like the actual period, right? The bump, right? It's like less than a second. It's probably like 0.6 seconds, right? Cool. So this gives you the period, okay? And here I will also define amplitude. Amplitude is the maximum displacement a single particle medium experiences. It's much more useful to define amplitude, not in terms of like, oh, how big is the wave, but in looking at the oscillatory behavior of a single particle. It's a much more precise definition that way. So this particle oscillates from being at equilibrium to like going below equilibrium and above equilibrium and above, and like displaced below and displaced above. And I'm going to define the amplitude as like the maximum displacement it ever experiences during this oscillation. And then that occurs here, and it occurs here, right? And that happens to be like, oh, that height and then that height, right? So that is how I define the amplitude. It's never like half of like the size of the wave. What an ugly definition. Cool. All right. That's it. Cool, huh? So really short 20-minute lecture. We're going to keep it short and sweet this week. The AP problem I gave today only takes probably 15 minutes, 10 to 15 minutes to review. If you have another problem that has similar topics, so anything related to simple harmonic oscillation and anything related to circular motion, please send it to me, and I will review that as the second problem, right? So our review session will last probably around like 30 minutes or something. Okay, so if there is another problem that you want to go over, if there's another problem that you would think would be useful to your classmates, if there's one you've already done, but you felt that it was really helpful and you want your classmates to get that same experience, send it to me, all right? And we can go over that problem as well, okay? So I'm gonna send a really short waves practice, okay? Really easy, really simple practice. It's due tomorrow morning. Super simple. And yeah, cool, all right? I'll see some of you at 7:30 tonight, okay? Have a great day. Bye.